Alright, find weighted median node in a tree. We are given an undirected weighted tree rooted at node 0. The number of nodes are 0 to n minus 1, and we are given to represent that tree, we are given edges, and each edge has a weight wi. Then we have a definition of weighted median node, which is basically uh, between two nodes ui and vi. The distance between the two nodes, suppose is x, right? Or suppose it's d, then half of that, the any node which is closer to the UH node and has a distance, total weight between ui and vi, divide by 2. That is, the distance between x and ui has a value that is greater than equal to half of the total weight between u and v. In that case, we call that node a median node. So we are given queries in which we have ui and vi, and we need to know median node for every particular query, right? So right off the bat, we can, if we know the concept called binary lifting, we can determine that that's going to be used here. But how is the question, right? So I will take a different approach. I just give a brief on binary lifting, and then I'll code that up, post that, because we are going to use the already given structures of binary lifting to basically solve this, the question specific part. So that's why having the template of binary lifting beforehand is going to help us a lot, because we are going to use those structure which we have already built for binary lifting, right? So what is binary lifting? Basically, binary lifting is an easy way of telling the nth ancestor, or telling what the nth ancestor for a particular node is, right? And we do it in powers of 2 so that we don't overwhelm in terms of memory. And the reason is, using powers of 2, like we do have bits, right? In bits we can use powers of 2 and easily determine every value or represent any value that is possible, odd or even or anything, right? Similarly, using powers of 2, if we store the ancestor of a particular node, right? For a particular node u, if we have something called ancestor of a particular node u, then we can have few ancestors, because we are dealing with powers of 2. So we are already compressing a lot of the ancestors by not having, not having them stored. So what we are storing is 2 to the power I number of ancestors for a particular node, right? And that boils down to 10 to the power 5 is the number of nodes that we have. So in worst case, if we are given a tree which is a straight tree, then the maximum jump that we can make is n jump, right? And this n jump is in this question 10 to the power 5. And since we are dealing with 2 to the power I, right, then the number of ancestors that we are going to store for a particular node is going to be this much, right? This much. And this is around 18 or 19, right? So that's the first thing. And having this stored, uh, basically we can do this using BFS or DFS. I'm going to use BFS. And during the BFS itself, we need to store something else as well. And what is that? Well, since we are basically using binary lifting to find out LCA between two particular node, right? What is LCA? LCA is least common ancestor. Suppose we have, right? If we have something like this and we are talking about node U and node V, this U doesn't look like U, and we are talking about the LCA of U and V. It can be this, it can be this, but we are talking about LCA, so the lowest common ancestor is going to be this, right? And we basically need to find this particular node. We don't know right off the bat that this is the node, right? What we have is the ancestor array, right, that we have already pre-computed. Using that, can I find the LCA? Well, we can. How? Uh, Basically using that ancestor array, what we can do is we can uh, when we were creating the ancestor array, right, what we can also create a prefix weight, which is going to store nothing but the distance of u from the root node, right? Distance of v from the root node. How does it help? Well, it helps in finding the LCA. So before moving to that part, let me show you how we are going to find the LCA. Suppose we have a better example will be this one. Right, suppose this is the US node, and we can know easily that this is at a level L1, this is at a level L2, and yeah, this is what, 1 2 3, this is 1 2 3. Yeah, so this is suppose we can easily find out, since we are already doing BFS for ancestor and prefix weight, we can always create a levels array which we can easily use to find out the level of a particular node using that particular array, right? So we are creating a lot of things, but that's what we need. This is another array or structure that we are going to create during the PFS itself. Now comes the LCA. So this is at a level L1 and this is at a level L2, right? They are different levels, and we can easily find out the difference between the level of V and U by basically subtracting L2 or L1 minus L2, right? And using the ancestor array which we have already created, we can jump that much difference, right? Using like we do in bits, you can use powers of 2 to generate that exact amount of jump, and using that ancestor array which we reach to that node, which will be this in this example, we see that now they are at level L2, both of them. Now what we can do is we can keep, or we can do the maximum jump that is possible, which is basically the calculation that we did, a log of 10, log 2 of 10 to the power 5 plus 1, and we see that we are going to reach a node which will be same for both of them, right? Because that's how it works. Above LCA, the ancestor of two nodes is going to be the same node, so we know that we have crossed the point of the LCA, right? Then we reduce the power, we see we again reach a point that is the same node, we reduce the power, and then we see that they have different nodes at this using this jump, right? Eventually we reach a point where the jump is small enough to not cross the LCA, right? We keep doing that till we reach a point where we can't jump further and the LCA is what we are at right now, right? So this way we have found out the LCA. So binary lifting helps us in another way. We can easily uh, tell the distance between two particular nodes. How? Now that we have already found out the LCA and we have created few things called prefix, weight and levels, right? We're going to use that, and basically if this is the node or this is the tree that we are talking about and this is the node we are at, we know that this is the LCA for this particular U and V that we have already calculated. So we need to know the distance between U and V. How are we going to know that? Remember that we already have a prefix weight. This prefix weight is going to be, it's going to tell us the distance of U from the root node, distance of V from the root node, and now that we have LCA, distance of LCA from the root node. How is that going to help us? Well, this is the distance that we want. This is the distance that we have, right? If we add this 1 and 2, then we are adding this particular part and we are adding this particular part twice, right? So if we do 1 plus 2 and minus the distance between the LCA, that is prefix weight of the LCA node, and we reduce it by 2 times. So this is a number, this is not the index. Let me find a better way to write this. So P1, that is this one, plus P2 minus 2 into P3 is going to give us this particular thing. Now we know the distance between U and V as well. Or we can just generalize the function and create a get distance function where we pass two nodes, right? Uh, and we can know the distance between any two nodes. Now let's code this up and then we are going to basically do the easy part now. This will be the easy part. This, what I just said, is the hard part, right? Alright, so let's code this up. We need few things. N, we need max power, right? I'll explain what is this. This is basically the max jump that we can do. This is the number of nodes. We already have N. So let me change this and make it global so that I can reuse it in different functions. We need max power. Max power is going to be what? Log 2 of N plus 1. We need the first we need to create the adjacency list so that we can do the BFS. So since we have weight, so it's going to be a 3D vector, and I'm sorry, we are going to iterate through the edges. ADJ of edge of 0 dot pushback edge of 1 and the weight, so edge of 2. And since this is undirected, it's going to be the other way as well, 0 1. So we have the Adjacency list ready. What we need is three things: the level, the vector or the ancestor, and the prefix weight. So ancestor is going to be for a particular node, different ancestors, right? So it's going to be a 2D vector. Let me call it ancestor. We need a distance vector which is going to store the distance from the root. So let me have long because this can overflow. Prefix weight, let me call this. And lastly, we need the levels array, right? So at this point, let me resize the array. I've declared it globally so that I can reuse in the different functions that we're going to create. This will be n, and this will be the number of ancestors that we are going to store for a particular node, and that is going to be determined by max power. It is going to be max power plus 1 or max power itself. So we are already doing the plus 1 here. uh, by default, for a particular node, right, without making any jump, this particular ancestor, let me have a default value of -1, right? This is important because this will be used as edge cases in the different functions. Prefix weight dot resize n comma 0. We have n number of nodes, so for every node the root distance is going to be stored here. Levels for all of them is again going to be resized for n comma, initially let me have -1, right? I'll explain why I did this. Basically, to determine if we have already calculated the ancestor for this particular node or not, I have used a default value. We have different ways of implementing this. Now we are going to populate these three things, right, using this BFS with binary lifting, right? So here we are going to pass the adjacency list. All the other things are already global. All right, so we are going to create a different function. Here, this is not going to pass anything. This is just going to populate the things with binary lifting. Here we are going to pass the adjacency list. All right, now we are going to do a BFS, straightforward BFS, where we have a queue. We are starting from the root node. The prefix weight for this particular node is what? This is the root node we are talking about, and in prefix weight we are basically storing the distance from the root node. So this is basically 0, right? So prefix weight of 0 is 0, right, which is anyways already 0, so we don't need to really write this, but just for explanation it's here. All right, so since we are basically doing a BFS, I'm going to go through different levels and basically assign and populate this particular array. For that I need level, which we are at. Let me write it later so that it's better explained. Now we are going to do a BFS, but before that, the levels of 0 needs to be populated. Is going to be the 0th level, right? While queue is empty, uh, we are basically taking the queue size and exhausting it, copying from the queue the node that we are going to compute, and I'm sorry, queue.pop for all of its neighbors, which is basically adj of node.size. We are taking the neighbor, right, and we are checking if this guy has already been computed, which we can use this value, default value, and see if this guy, so that we don't revisit a node, right? That's the reason I had this default value. So levels of neighbor, if it's equal to -1, then I am going to compute this particular neighbor to this particular level that I am at, which I don't have right now. So let me have a level which start from 0. Let me take this level and assign it here, and we are going to do that here as well for this particular neighbor node. Now we need to update the ancestors of this particular neighbor, which particular right. So the first, basically what we are storing is powers of two ancestors, right? So for particular node, ancestor of a particular node n or I can have 0, 1, 2. In this example it goes till 19, I guess, somewhere 19. So here the first, the zeroth jump basically means uh, the zeroth jump means one level up, right? Which in our case is going to be the node itself, right? Because the parent of this particular neighbor is the node, correct? That's why we created the adjacency list, so that we know which guy is the parent of which, right? Because we are starting at 0. This is an undirected edge, I understand, but we are given a valid tree which is rooted at 0. That's why we know this guy is the parent of this particular neighbor. So the 0th node is going to be the node itself. The next thing I need is the prefix weight of this particular neighbor to be calculated. That I can do it, basically prefix weight of this particular neighbor is the distance between the neighbor and the root, correct? Since we are already moving level by level, I know the prefix weight of node at this point, correct? That means prefix weight of node plus uh, the weight of this particular node is going to give me the distance, the added distance that we are going to have for this particular neighbor, right? This basically means that the distance of the node from the root plus this added distance, which is the weight for this particular edge, is going to be the distance for this particular neighbor from the root. So this is done. Now comes the part for the ancestor for the different jumps. We are going to populate it right here. So The zeroth level or the zeroth jump has already been calculated here. So let me call this jump. The zeroth jump is already calculated. We start from the first jump and we go till the max jump that we can do is that's the max power jump, right? We have it globally, so max power jump plus plus, right? So now comes the interesting part. So let me first write it and then I'll explain it. The parent node for this particular neighbor is going to be what? Uh, or actually not the parent node, basically ancestors of this particular neighbor at this particular jump is going to be what? This is just one jump above, that is going to be 0 for the first value, right? And we already have created that or know the value or the node for that. So we know the parent is never going to be invalid. If this parent is not equal to -1, which means if this parent has an ancestor existing, right, then ancestors of this neighbor at this jump, right, is going to be ancestors of this parent jump -1. This could be a little bit tricky, but what we are saying is uh, if this is a node and this is the uh, this is the node if we take a jump of this jump, right, and this is the test or the node that I'm going to trying to calculate for this particular uh, jump dash, right? So in that case, uh, since we are jumping in powers of 2, this jump is equivalent to this jump plus this jump, right? That's what we are doing here. Uh, this could be tricky, so let just go through it again. And this is the basically the crux of binary lifting, right? So what now that we have is we have already created these three structures and we need to move to the next or push this neighbor node so that we can calculate its children. So after this loop we can just queue.push this particular neighbor. I hope you can access, you know, this should be above in this loop. Yeah, yeah. So we are already having levels of neighbor being used for checking if the node has been visited or not, right? Now comes the part where we are going to use this ancestors array to determine LCA of a particular node. So for that we need few functions. The first function we are going to create is the distance function, right? So basically we are having a get distance function which takes two nodes and lets me know that this is the distance between u and v. For that, we are going to use the concept, and basically we need the LCA at this point. LCA, suppose we have a function get LCA, that's going to give me the LCA. It's going to give me the LCA between these two nodes, and I can use that along with the prefix weight array that we have created to know that the distance between u and v is going to be this formula. LCA, this is what we return. Now comes the part where we create the get LCA function, which takes u and v. Here we are going to check if both of them or both of the nodes are at a same level or not. So for that, I need to know which is at a deeper level so that I can lift it to the difference value, and then we can lift both of them together to find the LCA. Okay. So for that, I need to know the deeper node, which I can just calculate or know using the comparison between the levels of the two different nodes. If levels of u and v is this in this way, then we are going to swap and always keep the uh, I always keep the deeper, or how is it? Yeah. So basically, the difference between the two levels is created can be calculated here. Levels of u minus levels of v. Now I know the difference between levels of u and levels of v. Levels of u is always going to be the deeper one because we have set it up that way. Now u is going to be lifted and updated using basically a function called lift that we are going to create. This lift is going to create or return the node that we are at after being lifted by this much distance, right? So u is going to be lifted by this much distance or levels. So node comma the jump or the lift, right? Let me complete this one, and then we'll create or complete the lift function. So here, if u is equal to v, in that case we are talking about the same node, right? That means v was the LCA of u. Suppose u and v is this, or even better will be if u was this and v was this, then the LCA of u and v is v itself. So if we lift this much difference level, we make u this, so u and v is going to be equal here, and we are going to return any one of them. We can return u, right? Otherwise, I'm going to jump the maximum distance I can, or the maximum jump I can make, so that the node that I am at is going to be different, right? That's the jump I'm going to make. So the max power jump that I can make, and I'll keep reducing the power or the jump one by one, so that using this granularity or whatever, I basically reach a point where the ancestor of u after making I jumps, right, the ith ancestor of u is not equal to -1, which means uh, it is not the node itself. It is not a node which is invalid, right? And it is not the root node, right? If it is the root node, then we are basically at a point that we can't jump further. That's the LC. And ancestors of u of I, that is the ith ancestor of u is not equal to the ith ancestor of v. That means if they are not equal, that means we are at a point that uh, we have not crossed the LCA node yet. So we can jump to that point, making ancestors of ui, and alright, so now we can return ancestors of u of 0, right? We can return this now that we are at a point that they are equal. Ancestors of u of 0 is what we need. So we have the distance function, we have the get LCA, we don't have the lift function. So the lift is straightforward. Here we are basically jumping the exact amount that is passed, and this is going to return the node that we are going to be eventually at, right? So we basically uh, using the lift as a bit in terms of bits, we can see that what jump needs to be done in terms of power 2, right? Basically we have power which is initially 0, and we are going to check if lift is not 0, and we are going to basically look at this in terms of bits. Lift and 1, that is the uh, least significant bit. Is it a 1? If it is, then that power of jump needs to be done. That is, the node will be jumped to the power ancestor of node, that is node of power, and power will keep incrementing, and I will keep decrementing lift. Ultimately lift will be exhausted, and I'm going to return the node I am at, right? This is, I think, the entire BFS. We have everything that we need. Now basically we are going to do the last thing that is specific to the problem. That is, we're going to have answer is initially of size queries dot size, right? And for every query I am going to do what? Get the u and v that we need, that is queries of I of 0 and 1, and lastly we get the LCA. That's what we need. But now what we need to do is we have the entire structure ready, right? Now we just need to understand what we need to do, right? So we have a tree, right? Let me draw this properly this time. Let's say this is the tree. We are at here, the query is giving me a node u and a v, and I want to know the structure, right? Or I mean I want to know the median. So we basically need a node. Long story short, we just need a node between u and v. Correct? What we know already is the LCA of u and v. Basically, what we have done so far. This is the LCA, and I basically need the node respective to youth node. U is what I am interested in relatively, and not node v. Why? Because I'm looking a distance of total by 2 plus 1, or plus 1 by 2 distance far from you. Correct? That node should be at least this much distance far from this guy, you. So what I can do is do a binary search. Basically, this will be the first node, this is second node, third node. I'm considering a mid node, and I'm guessing that this is the node that has a distance of this much. I need to validate this case, and what I can do is I can just check the distance between u and mid and see if that distance is going to be t plus 1 by 2, right? And if it is t plus 1 by 2, then good enough. I am going to check for a node towards its left, because I want the closest node that satisfies this condition. I want the first node that satisfies this condition, and that's the reason we're going to do a binary search, get the second, third, fourth, or whatever node, and that's it. We have already used LCA to get the distance between any two node, and that's what we are going to do. So here I am going to have an answer. Initially, I can consider the vth node, because in worst case, by the way, in the constraint we are given that u and v will never be equal, I hope. I guess they can always be also be equal, but for conditions like we have only one edge between v and u, in that case we can always consider by default from the start v to be that node, right? Because I think the edge value is never going to be 0, if I'm not mistaken. Yeah, it's never going to be 0. It's always going to be the second node as my answer. So by default I can consider v to be my answer, and my start will be the 0th node. My end will be what? The total number of count. Total number of node count will be these 1 2 3 4 5 6. 6 are the total number of node count in the number of nodes I need to guess, right? How can I calculate that? We already know the levels of every node. I can use that, and I can basically do something like L of u plus L of v will be the number of nodes like this, number of nodes like this, and I need this number of nodes, so I am going to remove this part twice from this sum, minus 2 of L of LCA, and that's the reason we needed LCA to begin with. So what I can do is the number of node count will be levels of u plus levels of v minus 2 into levels of the LCA, which we already know that u comma v. This will give me the the LCA between u and v. And lastly, we are going to do the binary search. It's less than equal to end. Then midpoint will be start plus end by 2. The guest node is going to be what? This is the guest node, right? This is the middle node. I want the distance from this whatever middle node to the uth node. How am I going to calculate it? Well, I need to know the node in order to calculate the distance between that node and you. I just know this is the third node from the uth node. That's all I know. What we can do is we can lift u that many number of times to reach, and we can use the ancestors array to see what node lies here. But the problem is, what if the node lies in this branch? Then I need to lift v in that case, and that's the reason I need to calculate the node at this middle point. Let me call this get mid node from u. We are going to need u, v, mid, and LCA, right? So let's create that function. This is going to return integer node. We need u, we need v, we need the nth or the middle node, and we need the LCA. Alright, so this function get middle node from u. What we are basically doing is, or we are going to do is, suppose this is a tree, and what middle is, it's basically the node that we're selecting from 0 to the total number of nodes that we have at hand. So if this is the total number of nodes that we have at hand, I am guessing this to be that node. Or to keep things simpler, for now we are saying that this is the node, right? This is u, this is v, and this is the LCA. We already know what the LCA is by whatever we have already done, and I'm guessing this is the mid. Yeah, this is the mid. So what we need to do is I need to know what node this mid is, what node lies here, so that I can use that value and this to get the distance between them. And that's it. That's all I need to in order to validate if this is a valid node or not. If it is valid, I'm going to go more closer to you and see if it's still valid or not. If it is not, then I am going to go farther from this mid towards its right side, right? So how to know what node lies here? I can again use the ancestors array, but for that I need to know what jump I need to make. This is the jump I need to make, right? So what essentially I'm doing is I'm guessing that this is the first, second, or third, or the zeroth node. This is the zeroth node that we are saying. This is the first, this is the second. Suppose we are guessing that this is the second node. I want to know which node it is. I know the total number of nodes that I have, right? So I can just uh, yeah, I already know the total number of nodes, but which is not going to be required here because I need the second node. That means I need to make two jumps. If I need the first node, I need to make one jump. If there are more nodes here on this side of the LCA, on the left side of the LCA towards the U side, in that case, I just need to make the mid amount of jump, right? Otherwise, if this mid lies on this side, that is the number of nodes between LCA and U level of LCA minus level of U is going to give me the number of nodes here in this side, and if this value is smaller than mid, in that case uh, the mid lies towards the right hand side of the LCA, and this right hand side is going to mean that the mid lies here. I'm interested in this jump now because V is going to jump in order to know what node mid is, and this value can be calculated using let me clear this up a little. Yeah, suppose this is mid now. I'm interested in this jump and I know the total number of nodes, so I'm going to take the total number of nodes, subtract mid from it, and get this jump and make that jump using the lift array, and that lift array is going to return me the lift array is going to internally use the ancestor array and give me the node that I want, and that's it. That's what we are going to do. So I'm going to need actually the node count as well. So let me generalize this as the total node count. This is the total node count. I'm going to uh, yeah, I'm going to sorry total node count. I'm going to pass this. I could have recalculated it inside this function, but why to do that? So alright, so here I am going to check if the number of nodes towards the UH side, total nodes between U and LCA is equal to levels of U minus levels of LCA, because levels of U is always going to be a higher value than this. If this value is larger than mid, right, in that case or if it is also equal, then it's fine. In that case it lies on the left side or the UH side, and I can just return lift of U comma mid, else I can uh, let me call this required jump, or let's keep it that way. Now the required jump will be the total node count minus mid and lift of uh, required or V comma required jump, and I guess that's it. That's all we need. We are going to check now if the guest or the distance get distance, right? If that's the function that is your, let's see, get distance between u and v, get distance between mid comma guest node u comma guest node if it is less than equal to the target value, which is target distance is going to be total the distance between u and v. So get distance between u and v, divide by 2 plus 1. That's it. This is the target. If it's less than equal to target, then we are going to towards the left side, but also updating our answer. So let's have a sub answer. Or actually, let's update this guy itself. Answer of u is equal to mid comma or yeah, I'm going to go towards the left side, so end is equal to mid minus 1, otherwise I'll go right, start is equal to mid plus 1, and lastly I'm going to update the array, or it's already updated, so we are good. We can return the answer. Let's see if this works. Okay, this was a big problem. Let's see and fix all the errors. Alright, so I made a couple of mistakes here. This should be greater than equal to target and not less than equal to. This target can overflow, it should be long. Here I am basically getting the LCA, and here I am getting the distance, and instead that I am also again getting the LCA, so that is unnecessary. What I can do is take the entire get distance and take it outside and use it directly here, right? And I guess answer of I is equal to mid. That's not correct. We should have guessed node here, not mid. That's what we calculated. And lastly here, I guess somewhere the level is not incremented here. We have to increment level every cycle, right? And I guess that's it. Let's see if this works. There are other ways to implement it. I think binary search can also be avoided here, but it's easier using binary search. It just adds a logarithmic factor here. Right, this works. The time complexity will be, this will be O of n. This binary, so of your lifting population is going to be n log n, if where n is the number of nodes, and this guy should be q into, we are doing the LCA and the binary search. The binary search is going to be the dominant one, and this guy will be, since we have the distance function here as well, and the lift is also happening here, it's going to be log square n, in the sense log n into log n, and I guess that's going to be the time complexity. Q log n into log n is going to be the time complexity of this loop, if I'm correct. So that's the problem. Thanks.